Welcome. The topic we'll be discussing in this lecture is modulation. So before transmitting a digital data through a wireless medium, it should be first converted to an analog signal. Digital data are represented in the form of zeros and ones. So if you want to transmit it over an analog medium, over a wireless channel, it should be converted to an analog signal. So this process is called as digital modulation. This process is called as digital modulation. One of the example for digital modulation is modem. So modem is a device, modulator or demodulator. It converts the digital data from the computer into an analog form and it sends over the normal telephone connection, telephone line. Similarly, it receives data from the telephone line, which is in the form of analog, and convert it to digital form, and it gives to the computer. Similarly, for if you want to transmit any digital data over wireless medium, first it should be converted to analog form. And there are basically three methods of converting the binary streams to analog format. These methods are amplitude shift keying, frequency shift keying, and phase shift keying. So using these three techniques, using any one of this technique, and digital signal can be converted to an analog signal. But just converting a digital signal to an analog signal alone is not enough, because even after converting the digital signal to an analog signal, this analog signal cannot be transmitted over an wireless medium. After that, after converting the digital signal to an analog signal, we have to perform something called as analog modulation. We have to perform something called as analog modulation. What analog modulation does? So basically, uh, just converting a digital signal to an analog signal is not enough. Apart from that, after converting it to analog modulation is also required. So what analog modulation does in the sense, analog modulation basically shifts the center frequency of the baseband signal to the frequency of the carrier signal. That is the digital signal which you convert to analog signal either by using ASK, amplitude shift keying, or frequency shift keying, or phase shift keying. That signal is called as baseband signal. And that baseband signal should go through analog modulation. So this analog modulation, what it does in the sense, it shifts the central frequency of the baseband signal to the frequency of the radio carrier signal. So if we are so, so there are several reasons why this analog modulation should be done. Because if you are not doing analog modulation, so basically why baseband signal cannot be transmitted in a wireless system, in the sense there are few reasons, like say 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 in the previous say we have discussed about antennas. So something what we have discussed about antennas. So one of the characteristics of antenna is that the the height of the antenna, the height of the antenna should be should should be of the order of the magnitude of the signal's wavelength. Okay, the height or the length of the antenna must be of the order of magnitude of the signal's wavelength. That is, if the signal that the antenna is going to transmit or receive, if it is a 1 megahertz signal, then the antenna height should be more than 100 meters, which is practically not possible. But if the antenna is going to receive or transmit a signal of 1 gigahertz, then the size of the antenna can be of few centimeters. Okay. So this is the reason, this is one of the reason why the baseband signal should be converted to an should be should why the baseband signal uh, should pass through analog modulation, so that its central carrier frequency will move from baseband frequency to the frequency of the radio carrier, because the carrier frequency will be of higher frequency. So if the signal is converted to something of higher frequency, then the antenna size can be reduced. Okay, that is the first reason. And the second reason is frequency division multiplexing cannot be applied directly to a baseband signal. That is, just when you convert a digital signal to an analog signal by using either ASK, FSK, or PSK, that signal is called as baseband signal. And for a baseband signal, you cannot directly apply frequency division multiplexing. So at many places, we may want to apply frequency division multiplexing. If you want to apply frequency division multiplexing, then again, we need a signal of high frequency. And the third reason is the medium characteristics. So the medium through which the wireless signal is going to pass, this medium will be of different nature. Like there may be path loss, there may be reflection, there may be scattering, there may be diffraction. So like that, the medium, you cannot guess what type of medium it will be. So depending on the application, the right carrier frequency should be chosen. Okay. So depending on where it is going to apply it, accordingly, the signal should be modulated with the right carrier frequency. Okay. For example, if it is to be communicated through a submarine, then the carrier frequency should have a low frequency. The frequency of the carrier wave should be of low frequency. Okay. So like that, depending on the application, the carrier frequency will vary. So these are some of the reason why the baseband signal cannot be transmitted directly. Rather, it should go through a process, and that process is called as analog modulation. Okay. So, so what we have discussed so far in the sense, we cannot first, if you want to transmit any digital signal through a wireless medium, first you have to convert the digital signal to an analog signal. And that can be done by any one of the three techniques, which are amplitude shift keying, frequency shift keying, and phase shift keying. But just that conversion alone is not sufficient, because 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 after converting it to an uh, uh, analog signal, also the signal should go through analog modulation, so that the signal will be, the frequency of the signal will match the carrier frequency, and then only it can be transmitted. What we'll be discussing is the basic working principle of modulation and demodulation. What is modulation and what is demodulation? So this top diagram, this explains the concept of modulation. So with modulation, what happens in the sense? So first, here we are having the digital data, and digital data is modulated. So first, it goes through digital modulation. By performing digital modulation, so digital modulation means it applies any one of the technique, either amplitude shift keying, frequency shift keying, or phase shift keying. By performing any one of these technique, the signal will be converted to an analog signal. But this is an analog baseband signal. So as we know, the analog baseband signal cannot be transmitted directly due to various reasons. Like we have discussed, antenna size, frequency division multiplexing cannot be done, and depending on the medium characteristics, the carrier frequency should be chosen. Because of these reasons, we will not be directly transmitting the analog baseband signal. Rather, the analog baseband signal will go through a process which is called as analog modulation. So modulation will be always done by using a carrier wave which is of high frequency. So as the output of analog modulation, you will get a signal which is of higher frequency when compared with the analog baseband signal. Okay? And this high frequency signal will be transmitted over the wireless medium. This high frequency signal will be transmitted over the wireless medium. This process is called as modulation. And for demodulation, this high frequency signal which is transmitted by the transmitter will be received by some radio receiver. So this receiver, it receives the high frequency signal, and then it sends the high frequency signal through analog demodulator. Analog demodulator. So the analog demodulator will apply the same carrier which is applied by the analog modulation or analog modulator in the center end, and then it will perform demodulation, and it will separate the baseband signal, and it will separate out the baseband signal. So as the output of analog demodulation, in the receiver end we will get the baseband signal. Now this baseband signal should be converted to digital signal. So for that, some synchronization decision will be done, and based on that synchronization process, the analog baseband signal will be converted to digital data. So this process is called as demodulation. So this is how modulation and demodulation works with wireless communication. Let us try to understand the concept of amplitude shift keying. How amplitude shift keying works. So as we have discussed, there are three ways of converting digital signal to analog signal. So one of the method to convert digital signal to analog signal is amplitude shift keying. So here in amplitude shift keying, binary values of binary values 0 and 1 are represented with different amplitudes. Binary values 0 and 1 are represented with different amplitude. So you can see in this diagram. So if it is 1, it is represented with one particular signal with one amplitude. If it is 0, there is no signal. There is no signal. The amplitude is 0. Again, if it is 1, it is some other. So whenever there is a 1, the signal will be transmitted with one particular amplitude. If the value is 0, then no signal will be transmitted. So this is how amplitude shift keying works. It requires very low bandwidth, but it has some disadvantages, like it is more susceptible to interference. That is, it gets easily affected by noise or path loss or multipath propagation. So basically, this is not an efficient kind of modulation for wireless environment. Okay, so it can be used in wired network. So normally it is used with optical fiber communication. With wired transmission, it is used in optical fiber communication. Okay, so with optical fiber communication, if there is a light, it represents there is a 1. If there is no light, it represents it's a 0. Some rare places it is also used in wireless communication. For example, it is used with infrared transmission. For wireless infrared transmission, amplitude shift keying is used. Otherwise, generally, it is not a preferred technique for wireless environment, right? So the next type of digital modulation technique that we'll be discussing is frequency shift keying. So with frequency shift keying, what happens in the sense, uh, the, so here also we want to transmit the digital signal 0 and 1. So for transmitting 0, we use one frequency, say f1, and for transmitting 0 for 1, we use some other frequency, okay, say f2. Like that, there two different frequencies will be used with the same amplitude. Okay? The amplitude of the signal will be same, but the frequencies will vary. For transmitting 1, uh, we use one frequency, and for transmitting 0, we use some other frequency. And this is the most commonly used technique for wireless transmission. Frequency shift keying is the most commonly used technique for wireless transmission. The simplest form of frequency shift keying is called as binary shift keying. So in a binary shift keying, one is 0 is represented with one frequency, say or or anyway or any order. So 1 is represented with the frequency f1 and 0 is represented with the frequency f2. Okay, and so this can be easily implemented by using two different oscillators. One oscillator will be creating frequencies of f1 and another oscillator will be creating signals with frequency f2. So whenever you want to transmit a 1, use the first oscillator. Whenever you want to transmit 2, use the second oscillator. Okay. But when you switch from one oscillator to another oscillator, there is a chance that the phase of the signal may get changed. The phase of the signal may get changed. So to avoid such sudden phase changes, we can use something called as CPM, which means continuous phase modulation. The concept of CPM can be used to avoid sudden changes in the phase when you use an oscillator to change from one frequency to another frequency. And this diagram shows like how frequency modulation is done. So here maybe this may represent 1 and this may represent 0. So for 1 we follow one frequency. You may call it as f1. So this frequency you can call it as f1. And similarly, whenever you want to transmit 0, we follow some other frequency, which is f2. Okay. So this is how frequency shift keying works. And the frequency shift keying in the receiver end, what it will do in the sense, the receiver will use two band pass filters. The receiver will use two band pass filters. One is for f1, another one is for f2. A band pass filter is something which allows signals with frequency of certain range. Band pass filter is one which allows signals of frequency within certain range. So we'll be using two band pass filter. One band pass filter will allow only signals of frequency f1 within the range of f1, and another band pass filter will allow only signals within the range of f2. So as we know, f1 means 1 and f2 means 0. Okay, and then you can use a comparator. There is an electronic logic called a comparator, and comparator can be used to identify the strength of these two signals. Okay, the strength of the two signals which is received by both the band pass filters. So whichever the stronger signal, that will be 1, and whichever the weaker signal, that will be 0. So this is how the signal will be demodulated in the receiver end. So, so this is how basically frequency shift keying works. That is, it uses two different frequencies. It uses one frequency to represent 1 and another frequency to represent 0. Right. So the next type of uh, digital modulation technique that we'll be discussing is phase shift keying. So with phase shift keying, the phase of the signal will represent the data. Here the phase, here we'll use phase shift. Here we use the phase shift to represent the data. Okay. So the most commonly used phase shift keying is binary phase shift keying. So in a binary phase shift keying, there will be a shift of 180 degree. The signal will shift by 180 degree whenever there is a change from 1 to 0 or from 0 to 1. Whenever there is a change from 1 to 0 or 0 to 1, the signal will phase shift by 180 degree. For example, here this may be 1. This may be 1 and the signal is like this. Again here there is a phase shift. So, this is 0. So when it want to transmit a 0, there is a phase shift. Again it want to transmit a 1. So here again there is a phase shift. So you can see whenever the input changes, there is a phase shift. Okay. So this is the simple form of shift binary shift phase shift keying, which is called as binary phase shift keying. Okay. So this is how basically phase shift keying works. And in the receiver end, to receive the signal correctly, the receiver must synchronize with the sender. Okay, the receiver must synchronize with the sender's frequency and phase. Okay, and this is done by a technique called as phase lock loop, PLL. So this is the concept of phase shift keying. The next digital modulation technique that we'll be discussing is advanced frequency shift keying. Is advanced frequency shift keying. So this is an interesting concept. One of the so one of the advanced frequency shift keying technique is called as minimum shift keying. It's called as minimum shift keying, and this is a most famous scheme. Okay, so basically this minimum shift keying is also one form of binary frequency shift keying. This is one form of binary frequency shift keying uh, without abrupt phase changes. Okay, this is one form of binary shift keying without abrupt phase changes. So this is not with, it is without. Okay, let us change this. So it is without abrupt phase changing. So it is one form of binary phase shift keying without abrupt phase changes. So let us try to understand how this technique works. So here first the data bits will be separated into odd and even bits. The entire data bits will be separated into odd bits and even bits. And then we'll be using two different types of signals, two signals with different types of frequencies. One with a low frequency F1, the other one with a high frequency F2. Okay, so and then the frequency of F2 will be equal to twice the frequency of F1. The frequency of F2 will be twice the frequency of F1. Let us understand how advanced phase frequency shift keying works with an example. So here is the concept. Say this is the data which we want to transmit 10111010, right? So first we have to separate the even bits and the odd bits separately. So this is an odd bit, this is an odd bit, this is an odd bit, and this is an odd bit. Okay, this is an even bit, right? Or I'll use a different color for even. This is a even bit, and this is an even bit, and also this is an even bit. So first we'll separate odd bit and even bit. But for odd bit or even bit, now we'll use two clock signals. In the actual data, each bits are represented with one clock cycle. But after separating it to odd bit and even bit, we'll use two clock pulse to refer to one signal. Okay. So this is an odd bit. This is 1. So this is represented using two clock two clock pulse. So there are two ones, right? So this 1 1 here it becomes two ones, right? Similarly, next odd bit, which is also 1, so that is also represented using two ones. The next odd bit is 0, which is represented here using two zeros. The next odd bit also 0, which is represented using two zeros. Like that it continues. Okay. The first even bit is 1. The first even bit is 1. So here even bit starts. Here even bit start. You cannot mark it here. So here we are referring it with two ones. Okay. Here we are representing it with two ones. Okay. So as here it is 1, here all, sorry, the first even bit is 0. So here we are representing it with two zeros. As it is 0, this previous part also we are filling it with 0. Okay. So why this previous part is filled with 0 in the sense as this signal is 0, so it is filled with 0. If it is 1, it will be filled with 1. Okay. So this happens only for the even bit for the first time. So the first bit, the bit which precedes the first even bit will be the same as the whatever the whatever the value of that even bit. Okay. So this is how it is represented. Similarly, if you see the next even bit, it is also 0. So that is represented using the next even bit is 1. So that is represented using two ones. It is represented using two ones. Okay, so this is the next even bit that is represented using two ones. Again, the next even bit is also 1. So that is also represented using two ones. So this is how the odd bit and even bits are separated out. This is how the odd bits and even bits are separated out. Now, 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 as we discussed, there will be two signals with two different frequency. One with a low frequency, the other one with a high frequency. So this is the low frequency signal. So this is the low frequency signal, and this is the high frequency signal. Okay. So now let us see how minimum shift keying works. So with all these as inputs, so all these are inputs. With this, it should produce an output. So how this output will be produced? So the input includes the actual data and separation of odd bit and even bit, low frequency signal, high frequency signal, and from this the minimum shift keying signal should be created. So how it is created, in the sense it is created using the following this particular logic, which is shown in this right side small table. Okay. So here, first let me explain the nomenclature here used. Here H represents high frequency signal, N represents low frequency signal, plus represents original signal, and minus represents inverted signal. Okay. Wherever there is a H, it means the high frequency signal, this one. Wherever there is N, it represents low frequency signal, which is this. And wherever there is a plus, it means the original signal, the signal as it is. Wherever there is a minus, it means invert the signal. Okay. So this is how the logic works. If the even bit is 0 and also the odd bit is 0, then the resultant signal will be the high frequency signal. But the high frequency signal will be inverted. If the even bit is 0 and the odd bit is 0, the resultant signal will be inverted high frequency signal, because it is minus H. Okay, it will be inverted high frequency signal. If the even bit is 0, if the even bit is 1 and the odd bit is 0, if the even bit is 1 and the odd bit is 0, the resultant signal will be a low frequency signal, but it will be inverted. If the even bit is 1 and the odd bit is 0, then the resultant signal will be a low frequency, inverted low frequency signal. The resultant signal will be an inverted low frequency signal. If the even bit is 0 and the odd bit is 1, if the even bit is 0 and the odd bit is 1, the resultant signal will be the low frequency signal as it is. Low frequency signal as it is. If the even bit is 1 and the odd bit is also 1, then the resultant signal will be a high frequency signal as it is, the original high frequency signal. Okay. So with this understanding, let us try to sort it out, like how the resultant signal was created. How the resultant signal was created. Okay. So first let us see, like so we should know what is the even bit and the odd bit. So if you see here in the first clock pulse, even bit is 0, even bit is 0, odd bit is 1. Even bit is 0, odd bit is 1. If even is 0 and odd is 1, then the resultant signal will be the low frequency signal, original low frequency signal. Okay. So you see the original low frequency signal, it is like this. So the same thing comes here. The original low frequency signal as it is comes here. There is no change at all. Right. Let us move to the next clock pulse. The next clock pulse, the even bit is 0 here also, the odd bit is 1. It is same, no difference. So here also, if even bit is 0, odd bit is 1, then the resultant signal will be the original low frequency signal as it is. So the same low frequency signal comes here. Third case is also what even bit is 0, odd bit is 1. So the resultant signal will be the original low frequency signal, the same thing as as it is, it comes here. Okay. So let us see the fourth case. Here there is a change. Even bit is now 1, odd bit is also 1. Even bit is 1, odd bit is also 1. In that case, the resultant signal will be the high frequency signal, original high frequency signal. Resultant signal will be original high frequency signal. So you can see original high frequency signal is this. So the same thing as it is comes to the resultant signal. Okay. The next case, even bit is 1, odd bit is 0. If even bit is 1, then an odd bit is 0, then the resultant signal will be the inverted low frequency signal. Inverted low frequency signal. So this is the low frequency signal. If you invert it, it will come in the top. So it is just the inverse of the low frequency signal at that point. Inverse of the low frequency signal at that point. Okay. So similarly, the next is also 1 and 0. So this is also inverted low frequency signal. So this is the low frequency signal at this point. So invert it. Next is also 1 and 0. So here this is also inverted low frequency signal. So the low frequency signal at this point is this. So invert it. Okay. So this is how the minimum shift keying, which comes under advanced frequency shift keying. This is how the concept of minimum shift keying. Okay. I think it is clear. So the next topic that we'll be discussing is, so that is about advanced frequency shift keying. The next topic that we'll be discussing is advanced phase shift keying. Okay. Topic that we'll be discussing is advanced phase shift keying. So with basic phase shift keying, only one possible phase shift. Okay. That is 180 degrees shift is used to represent zeros and ones. Okay. So basically that is used with satellite systems. So whenever there is a zero, then the sine wave is transmitted as it is. And whenever there is a one, it represents the inverted sine wave. So with advanced phase shift keying, what we can do in the sense, the bit rate can be increased. With basic phase shift keying, only one bit can be transmitted at a time. But with advanced phase shift keying, the bit rate can be increased. The bit rate can be increased to a larger extent. Okay. So how it can be done? That's what we are going to discuss. So one of the technique of under advanced phase shift keying is QPSK. Okay. QPSK stands for quadrature phase shift keying. QPSK stands for quadrature phase shift key. Using this, higher bit rate can be achieved with the same bandwidth. Using this, higher bit rate can be achieved with the same bandwidth. So, so, so two bits can be transmitted at the same time. Whereas in binary phase shift keying, only one bit can be transmitted at the same time. But using quadrature phase shift keying, you can transmit two bits at the same time. That is called as two bits can be coded as one symbol. Okay. So symbol determines the shift of the sine wave. Okay. So when the two bits changes, when any one of the bits changes, then the phase of the then the sine wave will also change. Then there will be a shift in the sine wave. So this concept, quadrature phase shift keying, it actually needs less bandwidth when compared with binary phase shift keying. It requires less bandwidth when compared with binary phase shift keying, but it is a little complex to implement. Whereas the binary phase shift keying is very easy to implement. It is not easy as binary phase shift keying. Okay. So this diagram, you can see this top diagram, this represents the binary phase shift keying. Here there are only there is only 180 degree shift. Okay. So when there is no shift, it is 0. If there is a shift, it is, if there is a shift of 180 degree, it is 1. Okay. And with in quadrature phase shifting, quadrature phase shift keying technique, it always works based on a reference signal. It works in relative to a reference signal. Okay. So if the signal that you want to transmit is in phase with the reference signal, zero, that is represented with a zero. Okay, if the signal that you want to transmit is in phase with the reference signal, that is if it is same as the reference signal, that is called as in phase. So you say this is the reference signal, and the signal that you want to transmit, that is something like this. So that is also in phase, same, it is occurring the same time and same amplitude, then that signal is called as in phase. So that is represented with a zero. Okay. And so this diagram shows the quadrature phase shift keying. So here you can see there are uh, four possible shifts: 0 0, 0 1, 1 1, and 1 0. So this is in shift. So this is basically x-axis. So I mean this is uh, this represents in shift. This represents in shift, and 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 1 1 represents a phase shift of 45 degree. So this is in shift. Okay. So this is represented as 0. So to 0 to 1 1 you can see the angle is 45 degree. So 1 1 represents a phase shift of 45 degree, and 1 0 represents a phase shift of, so here the angle is 90 degree. Okay, so it represents a phase shift of 135 degrees. 1 0 represents a phase shift of 135 degree. And from 1 0 to 0 0, again it's a 90 degree. It represents a phase shift of 225 degrees. Okay, and and 0 1 represents a phase shift of 315 degrees. Okay, so this is how the signals were transmitted, right? So whenever there is a 1 1, there will be a phase shift of 45 degree. Whenever there is a 1 0, there will be a phase shift of 135 degree. Whenever we want to transmit 0 0, there will be a phase shift of 225 degree. Whenever there is 0 1, there will be a phase shift of 315 degrees. And that was explained in this diagram. So if you take a normal sine wave, if you take a normal sine wave, it's a complete sine wave. Sine wave will be like this, right? It will be like this. So if you cut at 45 degree, so this if you cut at 45 degree, then you will get something like this, right? You'll get something like this. So this is 1 1. So the cut is here because this 45 degree has gone, right? Okay. So if you, so because 1 1 means phase shift of 45 degree, right? If you cut at 135 degree, this is 45, this is 90. Okay, this is 135. If you cut it 135, it will cut here. So you are getting like this, right? Okay. If it is 0 0, then the cut will be at 225 degrees. So this is 180. This is 180. 180 plus 45 is 225. So then the cut will be here. Okay. So that this 0 0 is represented like this. Okay. And if it is 0 1, then the cut will be at 315 degrees. Okay. So 315 degrees means what? This is 225. 225 plus 45 is 315. So the cut will be here. Okay. So the next cycle of the sine wave will start. Right. So this is how the values are represented in analog. So whenever you want to pass a 1 1, this kind of signal will be transmitted. Whenever 1 0, this will be transmitted. Whenever 0 0, this will be transmitted. Whenever 0 1, this will be transmitted. Okay. So this is how basically advanced phase shift keying works. And here we have discussed about the quadrature phase shift keying, where there are two two bits can be transmitted at a time as a single symbol. Okay. So like this can be improved to any number of bits. Instead of 2 bits, you may also transmit 4 bits. Okay. So in the receiver part, how the receiver works in the sense the transmitter will select the part of the signal and concatenate them. So if it is 0 0, the signal will be what do you call? The signal will be shifted by 45 degree. I mean, if it is 1 1, the signal will be shifted by 45 degree, like that. Okay, like that, it will select the appropriate part of the signal and it will concatenate and it will send them. The receiver will compare the incoming signal with the reference signal and then it will regenerate the original signal. But here there is a drawback, there is a problem. The problem is the receiver should know the reference signal. The receiver should know the reference signal. So creating the reference signal at the receiver end is needs proper synchronization between transmitter and receiver frequently. Okay, because every time if the receiver has to create the reference signal, then the transmitter and the receiver should be synchronized frequently. I mean, very often. So this is the problem with uh, uh, this type of quadrature phase shift keying. But this can be avoided. But this can be avoided by using a technique called differential quadrature phase shift keying. So if you use differential quadrature phase shift keying, then 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 the receiver need not depend on the any reference signal. Rather the receiver can regenerate the signal depending on the previous two bits. Okay? Depending on the phase of the previous two bits, the signal can be regenerated. So like how here we use 2 bits, like that the number of bits can be increased. Okay. So next let us discuss another advanced phase shift keying which is called as QAM, quadrature amplitude modulation, which combines both amplitude and phase modulation. It combines amplitude and phase modulation. Okay. So using this you can code n bits as one symbol. It is possible to code n bits using one symbol. So let us discuss how 4 bits can be coded as one symbol. Okay. So there will be 2 power n discrete level. If n is 2, then it is QPSK. Okay. In quadrature phase shift keying, we send 2 bits at a time. Okay. So if n is 2, then it is identical to QPSK. So let us now understand how the uh, quadrature phase shift keying with let us try to understand how the 16 QAM works. 16 QAM. So using this you can send at most 16 symbols and 4 bits will represent one symbol. In the normal quadrature phase shift keying, we discussed 2 bits represents one symbol, but here 4 bits represents uh, one symbol. Okay. So in these schemes, as n increases, the error rate will increase, but it will have less errors when compared to phase shift normal PSK schemes. So, so this right side diagram, it shows the logic of how the 16 QAM works. Okay. So here you can see, uh, so 0 represents in phase, 0 represents in phase, and and you can see there are two numbers, 00011 and 0001. They both have same phase but have different amplitude. Okay. So this you can see 0011 and 001. They both have same phase. The phase of these two signals are same, but their amplitude is different. 001, this is the amplitude, whereas 0001, there is 0001, this is the amplitude. Okay. So this is how it combines amplitude modulation and phase modulation. But if you see this particular uh, sequence, 4 zeros and 1 000, 4 zeros and 1 000. So this is 4 zeros. This is 1 000. Okay. So they both have same amplitude. Here the amplitude is same. Okay. This is 0 0. This is 4 zeros and this is 1 000. The amplitude is same but their phases were different. Okay. So like this here you can see 16 symbols were represented as a combination of 4 bits. Okay. So like this it can be extended to 32 or 64 or any number of uh, symbols. But the problem is, as the numbers increases, what you call, the angle by which the phase shift happens will decrease, and hence there will be a possibility of more error. Okay, but still its error rate is less when compared to PSK schemes. Okay, so this is about QAM. Then the next kind of advanced phase shift keying that we'll be discussing is hierarchical modulation scheme. So here 64 QAM can be used with hierarchical modulation scheme. Even you can use 64 QAM. So 64 QAM, in the sense, it can transmit uh, six symbols. 6 bits will represent one symbol. 6 bits will represent one symbol. And basically this technique is used in DVB, digital video broadcast. This technique is used in digital video broadcast, and it uses 6 bits to represent a symbol. And out of these 6 bits, the two MSB bits, the 2 bits of MSB represents the QPSK signal. The 2 bits of MSB represents the quadrature phase shift keying signal, and the remaining 4 bits will be of QAM, quadrature amplitude modulation. Okay, so we discussed two techniques: quadrature phase shift keying, which uses 2 bits. The first thing, whatever we have discussed, and then we have discussed quadrature amplitude modulation with 4 bits. So this technique, 64 QAM, it uses 6 bits. Out of those 6 bits, first 2 bits of MSB where where which follows QPSK scheme, and the remaining 4 bits they follow QAM scheme. Okay, and how it works, in the sense, when the reception is good, if the receiver is receiving the signal with good strength, then the entire QAM constellation will be resolved. That is, all the 6 bits can be resolved properly. But if the reception is poor, that is, if the receiver is moving, then only the QPSK portion will be resolved. That is, the most significant 2 bits will be resolved. Okay, so this scheme basically it is used in digital television broadcast. So what it does, in the sense, the MSB 2 bits will be used to refer to high priority data of digital video broadcast, and that uses QPSK scheme, quadrature phase shift keying scheme. Okay, whereas the remaining 4 bits will refer to low priority data. Whereas the remaining 4 bits will refer to low priority data. So even if there is any issues, this low priority data will be ignored, but the high priority data will be recovered. So in case of television, high priority data will refer to standard resolution data stream. That is, the minimum standard resolution data stream will be referred using high priority 2 bits, which is given in the MSB position, and the low priority data uh, will be referred using the remaining 4 bits. Okay, so even if there is some signal if the signal is distorted, then the standard TV resolution can be received. That is, at least the at least the at least the standard resolution will be received, and the high resolution will be ignored. Okay, so this is how it works. So this diagram shows that. So you can see there are 6 bits to refer a symbol. The most significant 2 bits, it follows QPSK. The remaining 4 bits they follow QAM, quadrature amplitude modulation, and these contains high priority information, and this contains low priority information. In case of television, this contains the standard resolution, and this contains the high resolution. So if the signal is distorted, then this part alone will be at least recovered, so that the receiver can get the information at least in the standard resolution form, if high resolution is not possible. Okay, so this is how the various uh, digital modulation techniques works. Okay, so we have discussed modulation, the why the digital data should be modulated, how digital data are converted to analog data by using amplitude shift keying, phase shift keying, and frequency shift keying. And we have discussed advanced form of frequency shift keying, and several advanced form of phase shift keying like QPM, quadrature phase shift modulation, and QAM, quadrature amplitude modulation, right? So let us stop our discussion here. Thank you.